So let's actually get into the numerical example then. So here what I have, sorry if you have to squint a little bit, but here what I have is this two conductivity, or a composite material, all right? So on the left-hand side we have some, let's call it insulation. On the right-hand side we have some lumber. So this is maybe your wall, a wall or something like that. And on the top we're exposing it to some constant heat flux across the entire span. So you have this constant heat flux, and what heat is going to do is it's going to move from top to bottom, where you're sort of cooling by convection on the inner surface on the bottom. The fact that the insulation and lumber have different conductivities, though, means that there's going to be heat flow not just in the y direction, but also in the x direction. Because heat's going to want to move basically path of least resistance as much as it can. And so there's going to be like this tendency for the heat to kind of favor moving through the lumber as much as it can. You'll get this kind of gradient moving into the lumber from the insulation. So we're going to model this, right? If I was going to model this, I'd have to have PDE that governs my insulation. I'd have to have a separate PDE that governs my lumber. I'd have to have boundary conditions that I then apply both on the left, middle, and top boundaries, or left, middle, and right boundaries, as well as the top and bottom, right, for both of the domains. So that's a pretty complicated approach, right? It's a complicated multi-step solution process. It turns out we can basically just model this with one mesh, with one numerical mesh, and we're a little bit clever about how we do the conductivity, and we get a result. Okay, so let's go through how to do that. I'll warn you, fair warning, there's a lot of bookkeeping here, so the challenge is the bookkeeping. So pay attention to the little details as we go through. Okay, so what we can do to start is we're gonna start by discretizing this problem. So I need to discretize not only in the x direction, but also in the y direction. So let's start maybe, I'm gonna try to help myself here and zoom in. So I'm starting in the bottom left, and I'm gonna draw some nodes. So at the very bottom left corner, a little green dot I drew, that's node 1, 1. So this is node 1, 1. Let's start by discretizing in the x direction. So I've got maybe the first 3 nodes I've drawn. So how am I going to number this? I guess I have to decide on some convention, some numbering convention. My convention is going to be x direction is the first index, and y direction is the second index. So the numbering on this is going to be 1, 1, 2, 1, 3, 1, and so on. Now I'm going to also discretize in the y direction. So equal spacing in this case. So this would be, the one on the wall over here would be, 1, 2, right? X position 1, Y position 2. This would be 2, 2. And then let's say I draw another one up here, so this would be 1, 3. Right, so you're starting to get this mesh, or this set of nodes that's developing, and we're going to evaluate the temperature at each node, and that's going to form our set of unknowns. All right, so that's, let's see, that's the approach there. Let me maybe pick something in the middle. So in the middle, I could also just do this in terms of I. So let's do it like this. So I'm going to draw 9 nodes in a square. These are all equally spaced and have the same spacing as the ones in the bottom left, hopefully. So let's label these in terms of I. So the middle one, let's call this one I, comma I. So the one on to the right of that is going to be I plus 1, comma j. Sorry, I. The middle one is not I. The middle one is ij. So I'm going to use I as my x index and j as my y index, right? And then you can kind of see how this is going to go. So I minus 1j. Now above that's going to be I j plus 1. Below that is I j minus 1, and so on, right? You can just kind of map it out. let's see. So now you have an example of a corner node. You have examples of nodes in the middle. Obviously, you do this for the entire domain, right? So the nodes are going to line up with all the boundaries, the corners, and internally like this. The next step is going to be to draw a control volume. So I need a control volume for each node. Really what I need is one that represents the internal nodes. I need one that represents any other distinct node. So when you look at this problem, how many distinct patterns do we see? There's this one here, right, the internal node. There is this corner node here, right, because there's one side of it that's adiabatic and one side of it that's exposed to convection. This is a different pattern, right? The side is its own pattern. Up here is a different pattern. This one's exposed to flux. So in effect, you have to go around and survey where are all the unique conditions happening. And you should end up with a set of equations for the internal nodes. So it's like one energy balance applied for ij. So that's one. You have the four sides. So top, bottom, left, right. That's four more templates, basically. And then you have one for each corner. So, you know, all four around. So you're going to end up with, if my math is right there, that's 9. You have 9 different templates that you're using, right? So you have to kind of go through this control volume analysis 9 times.
Do we need to make nodes for the interaction between the lumber and the insulation?
Yeah, the question was, do you need to make nodes specifically to interact between lumber and insulation? In this case, no, I'm not going to do that. I don't think you generally would. The way I'm going to enforce this is we're just going to have some function that says if I is greater than, or if xi is greater than my limit, conductivity is one or the other. So it just sort of works out. You might want to do it so that the boundaries line up that way, just to keep it clean. But if you choose small enough nodes, it doesn't really matter. Other questions?
So you wouldn't want to put nodes along that boundary, right? You kind of want the nodes on either side to make it like linear.
Yeah, I think so. I mean, ultimately, remember these are like these are approximate models. So if you get to a point where it really matters, it's probably because you don't have enough nodes. So you just increase the resolution of the model, and eventually the answer is going to stop changing, and that's when you know you've done good enough. Yeah, good question. Okay, so let's do the control volume on the internal node. You'll kind of see how this plays out. So first, I've got to draw. Let's see. First, I've got to draw the control volume. So I'm drawing this to bisect the distance between the x and the y nodes, right? So if this distance up here is delta y, this distance here is also delta y. The distance between nodes is the y length of the control volume. And the same thing is going to go for the x. So this distance up here is going to be your delta x, same as this distance here. This here is delta x. Okay, so that's discretization. Now, in terms of like drawing what's happening, we're going to have heat flowing from node to node. So let's see what we have here. Yeah. So I'm going to draw the heat flow. Now I've got heat flow both in x and y. So I have to capture both of those things. So sorry, this is going to get even smaller. Let's do this. All right, so I have heat flow from the left. This is, let's call this Q dot left for node ij. In retrospect, I probably should have blown this up on a separate slide for you all if you're using my printout, so sorry about that. Okay, but anyways, we have a heat flow from the left. We have heat flow from the right, like this. Q dot R I J. We also have heat flow from the top, right here. Where am I going to put this? So this up here would be Q dot T I J. And we have heat flow from the bottom. So over here, this is Q dot Bij. If you happen to have like generation occurring, that would be G dot Ij. Okay, so we've identified all these terms now that are related to this 2D problem, and then we just have to go through, collect everything, and put it into a single energy balance. Okay, let's see. Before I do that, I just want to point out, just in terms of nomenclature, when I talk about the overall mesh, let's talk about the largest extent of the node. So the largest is going to be all the way to the right, all the way to the top. And I'm going to call this node M, comma, N, right? And there'd be obviously a mesh around that too. So Mn is my X and Y maximum extent nodes.